So here's a totally wild fact. A modern 7 billion parameter AI released today, it routinely beats out a 30 billion parameter AI from just 2 years ago. And no, the smaller model didn't magically get more parameters. It just got a better teacher. We're talking about a process called knowledge distillation, and it is honestly the quiet, brilliant reason why these tiny AI models have gotten so shockingly good.
Okay, let's dive into this. When you see a 7 billion parameter model today, completely holding its own against a 30 billion parameter behemoth from the recent past, the secret sauce isn't in its size. It's all in the training. Basically, the smaller model is learning directly from a giant AI. Now, the problem this solves is super simple, but, very real. Look, huge models know a ton of things, absolutely, but they're completely bottlenecked by their own massive scale. They're just too slow, and they're way too expensive to run from millions of everyday user requests. What we really want is a small model that behaves almost exactly like the giant one, but without dragging around that enormous size and staggering computational cost. To understand why this actually works, we've got to look at how we used to do things. The old way to train a small model was just incredibly rigid. You just show it ground truth labels. You'd basically say, this is a cat, and give it absolutely nothing else to go on. But the new way, knowledge distillation, it does something much smarter. It trains the small student model to perfectly imitate the large teacher model's full output. And importantly, that actually includes imitating its uncertainty. And this brilliantly illustrates what I mean. Instead of just giving a rigid black and white answer of cat, the teacher model spits out what we call a soft target. So it might say, okay, I'm 92% sure this is a cat, 5% tiger, 2% dog, and 1% other. All that extra statistical detail quietly teaches the student model how the teacher thinks, not just what the final right answer is. Think about it like how a master craftsman trains an apprentice. They don't just stare at a piece of wood and grunt, good or bad, right? They explain the nuance. They might say, this joint is strong, but the grain doesn't quite match, so fine for a workbench, but definitely not for fine furniture. That rich texture of judgment, rather than a simple pass or fail verdict, is what actually builds real skill over time. And that exact same principle applies perfectly to AI. A super confident output of 99% cat teaches the student something totally different than an uncertain, hesitant output of 60% cat, 35% tiger. By being exposed to all these highly specific gradations, the student model actually absorbs the real nuance of the master. So the crucial point here is the payoff. And wow, the payoff is dramatic. By using this exact technique, a student model doesn't just get slightly more efficient. No, it can literally be compressed down to just 1/10 the physical size of its teacher. But here's the crazy part. Even at just 1/10 the size, it can retain roughly 95% of the massive teacher model's overall quality while simultaneously running 10 times faster. I mean, really think about that for a second. You get almost all of the capability and reasoning power, but with just a mere fraction of the computational drag. This is exactly how the most impressive, modern, efficient models are being built today. Look at Microsoft's 5.3. It packs incredibly strong performance into just 3.8 billion parameters, making it small enough to run entirely on a smartphone. Google's Gemma 2, openly distilled from larger, more complex teachers. And Mistral 7B punches way above its weight class for this exact same reason. It really all comes down to this core idea. You don't need a giant brain running everywhere. You just need a giant brain to teach a small one once. And that leaves us with a fascinating question to consider as we wrap up this explainer. If artificial intelligence can learn this efficiently from a master, what other massive, cumbersome computing problems could we shrink down next?